Okay, folks, so this next question is 2020 question 6. It is the mechanics question. And as you can see, they've labeled all the questions with the different numbers. And we start off as per usual by answering a few definitions and a few recall questions. Here being definitions of Newton's laws of motion, show that F is equal to ma is a special case of Newton's second law, and describe an experiment to find the result of the two coplanar vectors. And then it moves into problem-solving questions. So first question we have there is state Newton's laws of motion. Take note of the fact that it says Newton's laws. So that tells us that there are three of them. First law tells us that a body will remain at rest. Sorry, let's move this up. Remain at rest or at a constant velocity unless an unbalanced force acts upon it. Okay, so that is what we have for Newton's first law. Newton's second law, do not write down F is equal to ma, write down the actual definition for it. So Newton's second law tells us that the rate of change of momentum of a body is directly proportional to the force that acts on the body, happens in the direction of the force, and is inversely proportional to the mass of the body. Okay, finally, the third law, and correct how I'd write this. I wouldn't write this as reactions, that every action has an opposite reaction. I prefer to write it like this. When a body A puts a force on a body B puts a force of equal magnitude on body A in the opposite direction. Okay, so the idea of I think like writing that every action has an opposite reaction, or every force has an opposite but equal force, I think they're kind of more summaries, but the more correct term to say is that when a body A puts a force on body B puts a force of equal magnitude back on body A in the opposite direction. Because Newton's third law always exists between two bodies with forces acting on each other. And I always like to highlight that out for my examiner as well. Okay, so the next question here, part 2, says show that F is equal to ma is a special case of Newton's second law. So this is going to be done as a derivation, and I'll show you all the steps that we have for that now. Okay, so the first thing we have to do is we reread our Newton's second law. So the Newton's second law told us that the rate of change of momentum was directly proportional to the force that was applied. So let's write out what that means in mathematical terms. The force is directly proportional to the rate of change of momentum. A change of momentum is mv minus mu, with mv being the initial momentum, mv being the final momentum, mu being the initial momentum. And because it's the rate, we divide it by time. So what do I do with this? I need to ultimately get this looking as F is equal to ma. That's what I'm looking as my final point. So I have a look at what I have here, and I can say that F is proportional. I can factorize out the mass on top. M bracket V minus U divided by T. So what I've done is I factorized out the mass from the top two terms. Let's rub this out of my way. If I look at what's inside the brackets tells me that V minus U over T. And if I look at my first equation of motion, V is equal to U plus AT. If I rearrange that, that gives me V minus U is equal to AT. And if I divide this by T and I divide this by T, those two actually will cancel out. That tells me that what I have inside my brackets I can swap in for A. So now I can write this as F is proportional to MA. And that's not exactly what I want, but it's looking very close to my final product. So I now write that F is equal to KMA, where K is a constant of proportionality. I know from the definition of a Newton, where 1 Newton is the force that acts on 1 kilogram of a body to give an acceleration of 1 meters per second squared. By that definition, that means that K has to be equal to 1. So if I just pop that in there, F is equal to 1 MA, and if I multiply that out, F is equal to MA. That gives me a full definition or full derivation that shows me how Newton's second law, which again states that the force is directly proportional to the rate of change of momentum, how that becomes a special case of force is equal to MA. Okay, folks, the next question asks us to describe with the Abel-Legel diagram an experiment to show the resultant between two vectors. So again, whenever you're drawing a diagram, or whenever you're drawing an experiment like this, they always want you to do 3 marks for your apparatus, 3 marks for your method, and 3 marks for your observations. So all diagrams, as per usual, drawn with a ruler. Don't draw a diagram without a ruler in Leaving Cert Physics. And also, when you're doing these, make sure your diagrams are big. There is no such thing as a diagram that's too big in physics, unless it goes off your page. There is such thing as a diagram, however, that is too small, because it won't be visible by the examiner. So get used to drawing these diagrams fast and labeling fast as well. Okay. So that's a Newton gauge. It's not my best piece of work, but it does the job. Okay, and sorry, just there we go, there's one. And then we draw another Newton gauge. And the final Newton gauge, I'll just draw coming over this way. Oh, that's just a little bit dodgy. Okay, so what you need to make sure is you need to make sure that you actually label all 3 of these again. So these are your Newton gauges. Okay, and this is just a string. And what I use is a metal ring. Okay, so this is the overall setup for how your diagram should look. So how do we do the actual experiment? Well, we have to draw in our method next. So the method is pretty straightforward. 1, set up Newton gauges, string and metal ring as shown in the diagram. 2, adjust the position of the ring and Newton gauges. Just makes it a little bit wider, so that the ring is stationary. 3, record the direction and magnitude of all 3 forces. Number 4, resolve any 2 forces using the triangle rule. And number 5, resolve, smooth this down a bit, my apologies, resolve the 3rd force with the resultant force. from part 4. And what you should observe at the end is when the ring stationary, all the resultant forces from steps 4 and 5 will cancel out to 0. Okay, so what we've done there is, let's just say we take this force here and this force here and we find the resultant, and let's just say it's moving to the left with 5 newtons. We will also find out then there should be 5 newtons acting to the right as well. So these two will have a component, so these two components will add together to give me the same force as this third one, just in the opposite direction, and that will work no matter what pair you pick. So if you pick this force and find the resultant, you should find it's the exact same force in magnitude to this force acting down to the left, except it'll happen in the direction to the diagonal top right. Okay. The next question we have now is part 4, and it looks at applying Newton's second law in some manner. So just one thing to always keep in mind, the definitions and or the experiments that we do at the start of a theory question usually always feed into the problem solving questions that we have that follow. So in this case, a cricket player moves her hands away from the motion of a ball as she catches it. So what that means is that the cricket player makes contact with the ball just around here, but as they make contact with the ball, they swing their arms down as they catch the ball. And as you can see, that means they're in contact with the ball for a longer time as they're catching it. So we have to explain why this is, and it tells us to explicitly use Newton's laws of motion to explain why she moves her hand away from the ball. So if we just go down and have a look at our little space, I'm going to look specifically at this part of the formula here. So we know that from Newton's second law that the force applied is directly proportional to the rate of change of momentum. And if I want to look at the relationship between F and T, that tells me that the force applied is inversely proportional to the time that the force is acting. So what this means is that if you have the force acting over a long time, the force itself is going to actually be lower than if you use a shorter time. So to explain that in words a little bit better, I just need to move this. Okay, so as the time of force acts is inversely proportional to the magnitude of the force, the longer it takes for the player to catch the ball, the lower in magnitude the force on their hands will be. So quite simply, the longer it takes to catch, the lower the contact force or the lower the impact force that the person is going to feel. The next part of this question looks at the problem solving. So it tells us here that the person playing cricket, she throws the ball upwards with an initial velocity of 28 meters per second at 45 degrees to the horizontal. Her hand was 1.6 meters above the ground. A short time later, the ball was caught by another player. When the ball was caught, it was again caught at a height of 1.6 meters above the ground. It asks us to calculate how long the ball was in the air. So guys, the first thing I would do when I look at a question like this is I would actually draw the information that they have told me there, so I can get a nice visual of what's happening. Now, these shouldn't take you very long to do, but they should give you an idea of what is occurring. So there's the ground. There's the ball. We know the ball is 1.6 meters above the ground when it is thrown. The person throws the ball at U is equal to 28 meters per second. That is at 45 degrees to the horizontal, as was told. We know the ball will take a parabolic curve under the force of gravity, and it will land once again at a point that is 1.6 meters from the ground. So that kind of gives me all the information that I want. Now it's asking me to find how much time is the ball in the air. So the way I look at this is I look at what information I have, and one thing that stands out to me is that the ball at the start is 1.6 meters in the air. The ball at the end is also 1.6 meters in the air, being in either the thrower's hand or the catcher's hand. So that tells me that its vertical displacement in total is going to be 0. I have a value for the initial, I can work out the initial velocity as well. But ultimately what I can do is if I take everything just in terms of its vertical motion, I can use S is equal to UT plus 1/2 of AT squared. Because I know that the overall displacement it has is 0, because it starts off at 1.6 and it ends at 1.6. So I need to find out how long it takes for it to come back to that particular point. The issue with this is right now, the U is in the vertical. So I need to just make a small addition to the question they give me. And I'll go back to this one here. And if I draw this out, I can see that I have 28 meters per second acting that way. But what I want to find is what is the vertical displacement happening in the y direction. So if I go back to my sine, cos, and tan, this is my 45 degrees here. So I know sine theta is equal to my opposite over my hypotenuse. And I'm trying to find the opposite, which is here. I have the hypotenuse there, and I have my sine theta, my angle theta there. So if I rearrange that, my opposite value is just my hypotenuse multiplied by the sine of theta. I can work that out really easily by putting my numbers in and then just plugging the numbers into a calculator. So my opposite, which is my velocity in the vertical direction, which I'm labeling Vy for the y-axis, is equal to 28, and I multiply that by the sine of 45 degrees. And then I just type that into my calculator, and when I type that into calculator, that will give me my vertical velocity is 19.8 meters per second. Now, just one thing, and I noticed it here, I'm using the letter V in this section. In my original formula, I used U. So I just have to remember that even though I've kind of slightly changed the lettering, this here is this here. Once I've done that, I can just again do a little bit more of the maths. And I'll go back to my original formula. Now, again, S is equal to UT plus 1/2 of AT squared. This formula is only talking about the vertical motion of the ball, not the horizontal motion. So it's only how long it takes for it to go up and go back down. It starts off 1.6 meters above the ground and it finishes 1.6 meters above the ground. So 0 is in for S. U is my 19.8 meters per second. T is the time that we're looking for, plus 1/2. And the acceleration, when a body is airborne and it's in motion through the air, the only acceleration it's feeling is the acceleration due to gravity, which acts in a downward motion. In this place, I'm going to put that as 9.8, and I'll make it negative to indicate that it is negative or acting downwards. So I put all my numbers out there. 0 is equal to 19.8 t minus 4.9 t squared. So when I've done that, this now just becomes a bit of a simple quadratic subquadratic factorization. I'm going to move everything over to the left, and that's going to give me 4.9 t squared minus 19.8 t. So again, the mathematical step was I moved this to that side of the equal sign, and I moved this to that side of the equal sign as well. That is now equal to 0. I see t's in common with both of them. So t times 4.9t minus 19.8. So I factorized out those two terms. And that tells me that my ball will be 0 meters from its initial point at time is equal to 0 seconds, which is the moment that the thrower lets it go. And also I can work out when the person catches it with 4.9t minus 19.8 is equal to 0. So then I just need to bring those numbers over and do a little bit of division. 4.9t is equal to 19.8. So what I need to do then is I need to divide both sides by the 4.9. And if I just do that on my calculator, that will give me a final value for the t of 4.04 seconds. Okay, so again, the idea there was we were trying to work out when does the ball come back to 1.6 meters above the ground, which means its overall vertical displacement is 0. So we used s is equal to ut plus a half at squared, and we found out there are 2 times when it's at that. At time equals 0, when the person is just throwing the ball, and at time is equal to 4.04 seconds, when they've just caught the ball. Okay, folks, so the next question then asked us, how far does the object travel in the horizontal direction? So if we take a quick look at our diagram here, we can see that the ball travels to a peak height and then back down to this 1.6 meters into the catcher's hand, and we worked out that takes 4.04 seconds. That also means that as it travels in the horizontal direction, the time it takes in the horizontal direction is also 4.04 seconds. So what we need to do is we need to work out what is the horizontal velocity and multiply that by the time, and that will tell us how far it travels in the horizontal direction. So having a look at our question, we know that velocity, or the average velocity, is equal to the change in displacement over the time taken. So in order for us to work out the displacement, or how far it travels in the horizontal direction, we just rewrite our formula. S is equal to VA times T. So because we are assuming that there is no air resistance and the horizontal velocity doesn't change, we just need to work out the initial value for the horizontal velocity, and for the rest of the question we assume that that was constant. So we know it is moving at 28 meters per second at 45 degrees to the horizontal. And we just need to work out this velocity here. So in this case, we can use cos theta, which is equal to my adjacent over my hypotenuse. And I'll just label this quick. That's my hypotenuse, this is my adjacent, and that there is my angle theta. So if I put my numbers in, cos 45 degrees is equal to my velocity, and that's going to be my average velocity in the horizontal direction divided by 28. So my average velocity in the horizontal direction is 28 times the cos of 45 degrees. That means my average velocity will have a value, if I do that on the calculator, it'll be very same as the last question, 19.8 meters per second. Okay. So what that now gives me is the opportunity to work out the distance that it travels. So like we said, we write out our formula. S is equal to V average times T. The displacement in the horizontal direction is 19.8, which is its average velocity, and that is moving for 4.04 seconds. So when I multiply those two numbers out together, that will give me a value for my final displacement in the horizontal direction. That gives me 79.99 meters. We can just average that to 80 meters. Okay. Okay, folks, so the last part of the calculation then asks us to calculate how far above the ground is the ball when it's at the max point of the throw. So we know already that it is 1.6 meters to here and 1.6 meters to here. And what the question is asking us to figure out is, what is the distance to this point here, where it is at the max point of the throw? Sorry, that's not the best diagram that I could have done, but that's the max point. So what we need to do is we need to find out from the throw, how far does the ball go from here to here. Now, one of the things we know about the ball is at this point, when it's at the max, that its vertical velocity, so in the y direction, is equal to 0. So it has, there's a moment of time there when the ball is not moving up, not moving down in the y direction, and that's when it's at the peak. So based on that, the easiest formula for us to work out is v squared is equal to u squared plus 2as. Because what that will allow us to do is that will allow us to work out the height, which I've labeled here with a small red arrow. So I'll put my numbers in. I know when I get to the top peak, v is going to be equal to 0. I've worked out earlier on, and I've already shown by calculation, that the initial vertical velocity is 19.8 meters per second. And I know that the ball is under the influence of gravity, which means A is minus 9.8. The value I'm looking for, S, is that little smaller red arrow, which will tell me how high above the person's hand when they threw it that it will land. Then start multiplying this out. That's going to give me 0 is equal to, and if I just square that number there, it gives me 392.04 minus, and if I multiply 2 by minus 9.8, that's going to give me minus 19.6s. So now I have a linear equation. I just need to bring the minus 19.6s to the other side and then divide. So that's going to give me, when I bring this term here over that way, it's going to give me 19.6s is equal to 392.04. And I'm trying to find the value then for s. So if I divide both sides by 19.6, divide that by 19.6, that means I will have a value of s. Just move this up a little bit. The value of s when I multiply that out or divide that out will be 20.002. So s is equal to 20 meters. What that has now told me, guys, is that when I move back up the top here, this little arrow here represents 20 meters. But we have to remember that was thrown out of the person's hand from 1.6 meters in the air. So I just have to then add on the actual 1.6 meters. If I add 1.6 meters, that's going to give me 21.6 meters, and that is my S total. The last part of the question tells us to draw a diagram to show the velocity v and the acceleration a of the ball when it's at its maximum height. Also show the force or forces F that are acting on the ball. Use the letters V, A, and F to label your vectors. Okay. So when we're doing this question, again, what it's looking to ask us to do is when the ball is at this point here, when it's at the absolute height, we need to draw the three vectors that are acting on said ball. Now, as we said previously in other parts of this question, we know that when it's at the peak, the ball does not have a vertical velocity, is only moving in the horizontal direction. So it only has a horizontal velocity. So when I draw my ball, when it's at the peak, it's not moving up, it's not moving down, which means in this case it's still moving to the right. So I will label that with my velocity there. The only force acting on it is the gravitational force. So I'm going to draw F acting down this way. And the acceleration that it's experiencing due to that force is A acting down that way as well. We also know that it's the acceleration due to gravity. So I'll just write at the bottom A is equal to 9.8 meters per second. Again, just to highlight exactly what that is.